Okay, I'll talk about near-coherent scrambling, and if we think about scrambling like scrambling to liquids, egg white and yolk, or ink and water, there are two ways to scramble them or to mix them. One way is to use a spoon, and this is a motion that is almost dissipationless. It mixes very efficiently. And the other way is through diffusion. And I want to make this point that there are two types of scrambling in many body systems. And the one that is almost dissipationless, almost coherent, is close to gravity, or at least to the black hole scrambling. First, let me introduce two main examples of scrambling with strong dissipation and scrambling that is almost dissipationless or almost coherent. The first one occurs at high temperature in a many-body system. So I'll write down a Hamiltonian and just show a qualitative picture. So if we have this Hamiltonian in a many-body system, there will be some coupling constants, say A, J, alpha, K, beta. And let me just call this capital J and that capital K to reduce the number of indices. So this is the Hamiltonian, and we consider the infinite temperature case, and write an out-of-time order correlator of this type. And to calculate this correlator, we evolve sigma j of t using the Heisenberg equation to 0 time, and write it in this form. Now, if we work at high temperature, say infinite temperature, then those numbers may be interpreted as amplitudes. And the sum of the squares of those numbers characterizes the norm of the operator. Actually, not the norm, but the expectation value of the operator squared. And the idea is when we evolve the operator backward in time, the size of the operator grows because the Hamiltonian turns a single sigma into 2 sigmas, then into 3 sigmas, and so on. And this sum will contain terms with many sigmas. The effective number of sigmas grows exponentially. And that's roughly the idea of scrambling at high temperature. This idea was described in the localized shocks paper by Lenin, Douglas, and Dan, and also by Shalian Chi. And let me introduce the other type of, maybe it's too dark here. I don't know, maybe I'll use this board. There is another type of scrambling that occurs in black holes. And the main idea is due to 't Hooft. Stephen Douglas work out the OTUCs in this picture, but this is the basic setting. This is a black hole in Kruskal coordinates U and V. And oh, yeah, I'm sorry. Yeah, maybe I'll use the other board. Yeah, I'll use just this one. So let's introduce a boundary, so it will be an ADS black hole to make the problem well defined. Just to make it easier. And we apply some operators at the boundary at time 0 and at time t. And let's apply x1 and x2 at time t, and x3 and x4 at time 0. And again, we apply them in an out of time order. So we want to know so 1, 3, 2, 4. Before we get to the out-of-time order correlator, let's discuss the basic mechanism that produces this correlator. When we apply x4 of 0, it creates some particles or excitations that fall into the black hole. And then we want to apply x2, and it's applied much later. When we go to a frame corresponding to the later time, it's like squeezing the picture this way and stretching it this way, so that point t is somewhere in the middle of the picture. And if we apply this transformation, this stuff becomes squeezed down to this line, the path horizon, and it becomes a shock wave. The gravitational perturbations produced by these particles become a shock wave. And there is another potential shock wave along the future horizon that will enter the picture, but in more simple terms, we're measuring a field that crosses the shock wave. And basically, the exponential growth of out-of-time order correlator is due to the scattering of particles going this way of the shock wave. And this is proportional to g Newton e to the kappa t and we should consider early times, and we should also make a connected correlator. So let me take this with a minus sign, and x1, x2, x3, x4 with a plus sign. Okay. The important thing here is that the Lyapunov exponent is close to the maximum value, to the Molesino-Schenker-Stanford band. And this correlator actually has a very special form. It's not just proportional to this number, it has a structure. And this is the general structure. This correlator can be written as C. It's a normalization constant. Let me put it to the -1, which is proportional to the inverse of G Newton. And it's a P out commutator X1 X2 P in and also it's imaginary, assuming that we have a certain normalization of P out and P in. What are these operators, P out and P in? These are some operators that act on fields, and P in is the null energy on the future horizon. And P out is the null energy on the past horizon. So there is a very special structure of this correlator. And my goal is to try to understand this structure, why this case is special. By the way, in the SYK model, the out-of-time order correlator has a similar form. P out and P in are SL2R generators, L plus 1, L minus 1. And P out and the constant C is of the order of n over beta j. Any questions at this point? Yeah.
This holds only at early times.
Yeah, that holds at early times. Okay, these are two main examples. Now let's think about a rather general situation. Suppose we have a many-body system that is like that system, many interacting spins or many interacting fermions, and we're making an assumption that these are all-to-all interactions, so that there is one principal mode in the system. We don't care about spatial dependence of various quantities, only about the time dependence. So if something grows in this system, it grows only in time and it's homogeneous in space. So this is the main assumption. And we'll try to understand the general form of OTOCs and interpret them in terms of scattering metrics and in terms of the so-called retarded kernel. First, let's try to think about out-of-time order correlators formally and write some very general expression one can expect in the situation where there is only one exponentially growing mode. So once again, we use x1, x2, x3, x4 minus, or plus will be for fermions, minus for bosons. Now, let me use complex time, and I'll introduce this notation. Beta will be 2 pi, and the maximum value of the Lyapunov exponent is 1, so next we use dimensionless time theta it, and write all the operators in terms of this complex time. And in principle, one can define this thing for arbitrary thetas. The only condition is that they should be correctly ordered on the circle. So the real parts are like this. Or we can use this this thing, this variable, and draw those thetas in terms of and normally they would be on a circle, but I want this condition. Theta 1, theta 2 is it, and theta 3, theta 4 is about 0. And in this picture, and time goes inward. So this ordering 1, 3, 2, 4 is with respect to the angular coordinate, and the radial coordinate can be arbitrary. And this condition, when p is much greater than 1, means that 3 and 4 stay at the boundary, at the unit circle, and 1 and 2 are pushed inward. So 1 and 2 will be very close to the origin. And we can write a guess for this quantity. It's not such a wild guess. It's just based on the assumption that this quantity grows exponentially with a certain exponent. We can write that this should be proportional to c to the minus 1, just a normalization constant. Next, there will be something peculiar, but I'll explain. It's I kappa pi minus theta 1 minus theta 2 plus theta 3 plus theta 4 over 2. And this will be multiplied by a vertex function, gamma of x1, x2, so now this is the cartoon. We have 1 and 2, 3 and 4. These points are in the past, those are in the future, and the interaction is propagated by some mode. Let's call it Scrambling, and this function is the propagator, and these functions are vertex functions. The first one will be retarded, and the second one will be advanced. So how do we get this expression? The general dependence is on 4 variables, theta 1, 2, 3, 4. However, if we add a constant to all the variables, nothing should change. So there will be dependence on the difference of theta 1 minus theta 2, which is here, and also of theta 3 minus theta 4. And we hope that these two functions decouple. So it's actually a product of two functions. One depends on one variable, the other on the other variable. And there is also some dependence on the center of mass of 1 and 2 and center of mass of 3 and 4. And this is in the exponent. And if we plug IT for 1 and 2, theta 1, theta 2, we get the right growth with exponent kappa. And this quantity pi is introduced for convenience because this way this expression is symmetric. And I'll be using some arguments from the paper by Moldasena, Schenker, and Stanford about the upper bound of the Lyapunov exponent to argue that this coefficient is real, and there are some symmetries in gamma R and gamma A, and also this coefficient is positive. Of course, I'm not going to tell you all the arguments, but here is the general idea. If we put these points 1, 2, 3, 4 in a symmetric position, the symmetric is this. This configuration has a reflection symmetry about the horizontal axis and about the vertical axis. And those symmetries impose certain constraints on gamma R and gamma A. And in this particular case, the imaginary part, the real part of this expression vanishes, or the imaginary part of the exponent vanishes in the symmetric case. And that's why the constant pi is here. So if we use the symmetric configuration and make all those operators 1, 2, 3, 4 Hermitian, and furthermore, if we use the same x for 1 and 2 and another operator for 3 and 4, this is the maximally symmetric case. Then we can argue that this quantity should be real. That's why the coefficient c to the minus 1 is real. And there is another more subtle positivity argument. For the positivity argument, one has to use two different things. Instead of putting 1, 2, 3, and 4 in a symmetric position, one should rotate 1 and 2 either this way or the opposite way. And in this case, there will be some additional symmetries that allow one to argue about positivity. So let's proceed this way. Let's find some symmetry conditions, not the positivity condition for x1, x2. If we take the Hermitian conjugate, it's in another symmetry condition, if we turn theta to pi minus theta. The first one follows from the vertical, from the reflection about the vertical line in the symmetric position. And the second one follows from the 180-degree rotation. And if we combine these two equations with the general form of the correlator, we can find something interesting. We can find the commutator, the correlator between the commutators. X and that is equal to 2 cosine kappa pi over 2 divided by c. And the rest of the expression is the same. Now, I'm sorry, I should actually write down the arguments, because the commutator cannot be defined if the real parts of theta 1 and theta 2 are different. The commutator should be defined for x3 of 0. Maybe I'll just copy from my paper. Now, notice that there is this cosine factor. And the cosine factor comes about because we expand the commutator into 2 terms, and the second commutator into 2 terms. 2 of the terms, 2 of the 4 resulting terms will not be out of time order. And for large time difference, they factor. And they roughly correspond to the first term there. And the out-of-time order terms will be in 2 positions. I drew those arrows rotating 1 and 2 clockwise and counterclockwise. And one gives e to the I kappa pi over 2. And the other gives e to the minus I kappa pi over 2. And this explains the numerator in this expression. So the conclusion is when kappa has the maximum value, then this thing should vanish. And this argument is actually due to Douglas and Yunfei, the basic argument. They did it in a more special case using equal operators in this expression and in this expression. So, but on the other hand, the argument was more general in the sense that they didn't use the ansatz. Anyway, one can analyze this expression in the case when kappa is not exactly 1 but close to 1. And we have one small number here and another number. In the SYK model, both the numerator and denominator are proportional to the. Okay, I'll write it down. In the SYK case, 1 minus kappa is of the order of n over 1 over beta j. And C is of the order of n over beta j. And when beta j goes to infinity at extremely low temperature, both the numerator and denominator go to 0. But this thing has a finite limit. So I've written many expressions here. Let me just summarize this part of the talk. From general arguments, we can figure the form of the out-of-time order correlator. And the out-of-time order correlator for the commutators may be qualitatively different when kappa is close to the maximum value. It's much smaller than the usual out-of-time order correlator due to this factor. And in the rest of my talk, I'll argue why this factor may be called the decoherence factor. Yeah.
In general, you have a sum over different types, or like in general, we are doing decomposition of the formal sum, and we effect get a sum over such terms.
Well, I haven't really thought about the sums. Actually, I did think about sums, but it may be more complicated if there is a degenerate case when the Lyapunov exponent is exactly the same. So I'm not completely sure what will happen then. The problem is that you'll see that actually it's already in this formula. There is a cancellation of two small quantities. And when such things occurs, one should be careful about degenerate cases. Or maybe I'll use this board. So let me interpret this thing as decoherence. And this is related to the scattering matrix. So usually we define scattering matrix, S-matrix, as a relation between in and out states. But one can also try to define an S-matrix in the following way. Suppose we have a full theory of something, say a field theory, and another theory, an effective theory or a naive theory that only has stable particles. And those particles don't interact. And one can embed the Hilbert space of the naive theory into the Hilbert space of the full theory in two different ways. Suppose we take a state of, say, a proton and an electron in the naive theory, and they can be on top of each other. We don't care, because in this naive theory, they don't interact. We evolve them back in time. They become separated in space. Then we can identify them with excitations in the full theory and evolve them forward in time. And this is one embedding. Another embedding, we take the same state, evolve forward in time, identify with actual excitations of the field theory, and evolve back in time. And the S-matrix is the relation between these two embeddings. So one uses evolution to the infinite past, the other uses evolution to the infinite future. In my interpretation of scattering for a thermal system, I'll not use infinite past and future, but rather time-ordered products and anti-time ordered products, not out-of-time ordered products, just these two. And if we fix the arrow of time, say time goes forward, we can construct a nice embedding of a naive theory into the full theory. And I'll give an example of a naive theory in a moment. If we decide that time goes backward, we can construct another embedding of the naive theory into the full theory. And the S-matrix will describe the relation between these two embeddings. However, in thermal systems, there is a big difference from scattering and field theory. In thermal systems, the S-matrix is generally not unitary. And the case where kappa is close to 1 corresponds to the unitarity limit. So when kappa is 1, then the scattering is unitary.
Wouldn't the same effect happen in an ordinary theory if you are just neglecting some of the states? Flat space, because in flat space we have a similar story in the Regge limit. And these imaginary parts that you are discussing are like the creation of strings and so on.
Right. Here is my understanding of this effect, although I don't know string theory, so I might be wrong. So my understanding is this. In this picture, we scatter particles. And it's not that we're neglecting states. It's the thing that some states cannot be described entirely in the physical region. We would like to work in the physical wedge, which is on this side. And if all interactions were perfectly local, then it would be a consistent description of things that are only on this side. However, if there is some non-locality in the theory, and we're formulating our embeddings using only the right-hand side, then we'll inevitably miss something. And including more states into this theory of the world on the right-hand side won't help unless we include everything.
The same formula is called for scattering of particles in flat space.
Mm-hmm.
There, what you're neglecting, I mean, these imaginary parts come from the creation of intermediate string states. So some new intermediate states that are not the right ones. Those states are long-lived, and that's the interpretation of this cosine and so on that we're discussing, at least in that context.
Yeah, I understand. But let's consider a black hole. And suppose the scattering happens in a black hole. The black hole is used as an accelerator so that we can have high energy collisions. There are two different points of view of the black hole. One is at short times, of the order of scrambling time. And the other is at times as long as Page's time. In the second point of view, we can see all particles coming in and all particles going out. And in this case, nothing is missing. However, if we work in a short frame of the order of scrambling time, something will be missing inevitably. And this is a guess. I don't have much to support it, but I'm guessing that including more degrees of freedom in our theory won't won't help unless we include everything, basically, and go to the full picture that allows the description on very long times, like pages time. So if we work in a short time interval, then something is missing because there is a non-locality between the right wedge and the left wedge. And an attempt to construct a consistent theory of the right wedge must fail. But this is just a guess. Now, maybe I'll just write a tentative definition of a naive theory. A naive theory can be a theory of an oscillator path. So suppose we have some system of spins or some system of fermions, and we pick a few degrees of freedom we can use to probe the system, and the rest of the system will be a heat bath. It's important that the system is at a finite temperature. At zero temperature, the problems I'll describe do not occur. So it's a heat bath. And one can write an effective Hamiltonian this way. Little n is the number of degrees of freedom that are included in the naive theory. And these are the degrees of freedom. And chi sub j belongs to the bath. So this is some combination of other degrees of freedom in the system. And the naive, these bath variables can be characterized by their correlation functions. And one can write something like this. And this is self-energy, but self-energy is the same as self-energy for the actual degrees of freedom is the same as the Green function for the bath variables. And one can assume in the first approximation, it's a good assumption that these are free fermions. They obey Wick's theorem. And the naive theory will be a theory of free fermions with a given correlation function. Those fermions can be described, in the case of the SYK model at least, as bulk fermions. One can view chi sub j as bulk fields in ADS, and actually there is a field in the bulk, and chi it's not entirely correct. I'm writing psi b equals 0. It's like the Dirichlet condition. But since it's a fermion, it has two components. So one has to write it more accurately. But morally, it's this. It's the Dirichlet boundary condition for the field psi. and chi is the derivative of this field at the boundary, and sorry, xi, and chi lives strictly on the boundary. Now, when we couple the chi field, the boundary field, to the boundary value of the bulk field, this changes the effective boundary condition for the chi field, for the xi field, or psi field. And the Dirichlet condition effectively changed to Neumann condition. So one can think about the correlator without those chi's, the boundary fields. And the boundary condition in this case is Dirichlet. When we add the boundary degrees of freedom, the boundary condition changes to von Neumann. So this is a model of the heat bath, but for the following discussion, it's not necessary to have such a detailed model. We can just assume that there is some kind of bulk which is just a set of harmonic oscillators, fermionic oscillators. So the heat bath is a set of free fermions, and we construct two embeddings of the Hilbert space of free fermions to the Hilbert space of the full model. Now, the Hilbert space of free fermions is deduced from the correlation function. And there is a mathematical definition of that Hilbert space using the Guilfand-Nyberg-Siegel construction. This Hilbert space is infinitely dimensional, and we cannot possibly embed it into the Hilbert space of the actual model. However, we can embed those states that have few particles. So the vacuum of the naive theory is the same as the thermophile double state, and it comes naturally in the Guilfand-Nyberg-Siegel construction. The associated state of the full theory is also the thermophile double. And we can create some excitations on top of the thermophile double in the naive theory. And remember which apparatus we used to create the excitation, and use the same apparatus in the full theory. This is the recipe of the mapping. However, there is a choice. If the same excitation is created in the naive theory by applying apparatus in the time order, and we apply the same apparatus in the full theory in the time order, then their correlation functions do not exactly match, but almost match. This is one embedding. If we apply apparatus in the reverse order, this will be another embedding. In the naive theory, it doesn't matter. If the separation between two times is very large, it doesn't matter in which order we apply. In the full theory, it does matter. So there are two different definitions of embeddings, and one can construct for example, X and we call this thing S out, and this thing S in. Now, as written here, it looks meaningless because I haven't defined the full structure on the left-hand side. This thing, written in brackets, is just a record of the operators that have been applied, and the non-trivial information that needs to be supplied is the inner product. And the inner product is given by the expectation value in the naive theory. Similarly, when we have this state in the full theory, we also need the inner product. And the point is, when we use the first rule and calculate the inner products in the naive theory and in the full theory, they're almost identical. If we use the second rule and calculate the inner products in the two theories, they are almost identical. But if we start mixing them, they are no longer identical. If we calculate the inner product between this state and that state, that inner product differs significantly from the naive theory prediction. And this way, we have two distinct embeddings. The first embedding, I call it an embedding exactly because it almost preserves the inner product, and same for the second thing. But it would do S in S out dagger and call it S. That is a non-trivial operator. And different types of out-of-time order correlators can be interpreted as matrix elements of this matrix S. And this thing is X, maybe it's 2. And the commutator thing is this. So this type of O2C has 1 minus S, and this is a different expression. If S is unitary, then that expression now, if I assume that this thing is of the order of lambda, then that thing is proportional to lambda squared. So if S is unitary, then the commutator O2C must be much smaller than the general O2C. Lambda much smaller than 1 is the early time assumption. At early times, both O2Cs are small, but the first one is proportional to lambda, and the second one is to lambda squared. That is based on unitarity. And conversely, if we have in some concrete system the same scaling of the first type and the second type of correlators, then the S-matrix must not be unitary. And of course, okay. Right. So this is one conclusion that the S-matrix defined this way shows the difference between the two types of scrambling, like the diffusive scrambling, where the S-matrix is non-unitary, and the coherent scrambling where the scrambling is unitary. And another thing I just want to mention, using the ladder kernel, one can actually derive some identity that involves exactly that factor. 2 cosine kappa pi over 2 divided by c is related to some quantities expressed in terms of the ladder kernel. In particular, the so-called k prime, k retarded prime, enters this expression, and it's interpreted as the branching time. It's the time needed in the first picture to generate a new generation of operators. If we, in the first picture, think about evolution as a branching process, one can define the branching time, and it enters a formula for that quantity. Yeah, that's basically it.